Okay, so we're going to be going through this file. This is the featurize.py file. I'm going to explain what most of it does, try to go through line by line and just give you the gist of it. I'm not going to go too far into specifics. These first 5 lines are just libraries and modules, NumPy for array math, pandas for reading CSVs, collections for defining a certain dictionary down here, RE for regular expressions. This will be used to sort through chemical compositions in a quick way, and then TQDM for progress bars during like for loops and stuff. All symbols represents all of the atomic symbols for elements that are valid. If something isn't in this list but is returned from one of our searches, we can tell people, hey, look, this had a symbol in the chemical formula that we didn't recognize. Composition error, this comes from the PyMatGen library. This code, um, this class, and these functions here, so get symbol dict function, parse formula function, and fractional composition function, element composition function. Those 4 functions all come from the PyMatGen fractional composition module. I just kind of copied them over to here because they're convenient and well done. So we're going to do everything within the class featurizer. So we're going to make an object that holds all of the information associated with a data set. So when you initialize this object, we're going to read in a file name. And that file name for us is going to represent the, so here's us creating this object, the class featurizer, reading in a path. This is going to represent our data with the chemical formula we want to be featurized in the first column. So upon initialization of this object, we give it a file name, and it's going to define a data frame associated with that file name. So this is a pandas data frame, think an Excel sheet. What getSymbolDict is going to do is it's going to take a chemical formula that's been, I'll call it flattened, so there'll be no more parentheses or anything, that'll be parsed, and it's going to turn that chemical formula into a dictionary. So in our case, if we had like H2O, it'd be a dictionary with H in it. So look over here now, I'm just going to make a quick example. The dictionary with H in it, and there'd be 2 of them, and then O in it, and there would be 1 of them. So it's going to take in the string H2O or O1, either of these would work, and it's going to make that dictionary. Now to get that string, we're going to use Parse Formula. So what Parse Formula is going to do is it's going to first replace brackets with parentheses, like this at sign for metafluorine, metallofluorines. This comes again from PyMatGen. I've just added a little bit to it, like the replacement of brackets. And then what it's going to do is it's going to look for the innermost parentheses. So if I have A, B, or A, B, and then inside that is like C to D, or if I have this here, what it's going to do is it's going to look at this innermost parenthesis the first time through, and if it finds an innermost parenthesis, it's going to essentially factor it out. So this is going to become C8 and D4, and we'll get rid of that 4 there. And then it can get rid of that parenthesis, and then it'll repeat itself. So at the end, it's going to call itself again. So then it'll look at the new formula, and it's going to now factor this 3 in. So that'll go here, that'll go here, and that'll go here. And then this would be a fully flattened formula. There's no more parentheses in it. And so that would be passed into getSymbolDict to get the dictionary that would be like A with 1, B with 3, C with 24, and D with 12. So this is used. So I call this on a complicated formula with parentheses and stuff, or it doesn't even have to have parentheses. But if it has parentheses, it goes through this section of the function. If it doesn't, it simply calls getSymbolDictionary. Okay, so now these functions, fractional composition and fractional composition L, this returns the fractional composition as a dictionary. This returns the fractional composition as a list of atoms and a list of the atom counts. So in our case, we would have either a dictionary, we just go, so it'd be like A1 and B3 dot dot etc. So we have that, or what we would have is that first one is fractional composition, that returns the dictionary version. The second one is fractional composition L, which returns the 2 lists. So in our case, it's going to be A, B. So that'd be our first list, and then everything else in there. And then we'd get a second list that's returned. That would be the 1, 3, 24, and 12. So that's fractional composition L. And so this is my slight modification to the PyMatGen function of fractional composition. And then element composition does the same thing, but instead of giving it fractionally, so I suppose all of these should be divided by the total number of atoms in there, it gives the full numbers. So fractional would actually be, let's see, there's 1 plus 3 is 4, 28, and then 30, 40. So A would actually be 1 over 40 if we were to look at fractional composition in this list. So it'd be like A, 1 over 40, and then B, 3 over 40. So this would be fractional. And then if you do element composition, it just straight up grabs the 1 and the 3. So it doesn't normalize it by the total number of elements. Okay, and then assigned features, what this is going to do is this function takes in a list of matrices, element information, and formula. There's perhaps a more complicated part of the function. These two that I built, they're not quite as streamlined. And what it's going to return at the end of it is I call it a composition matrix. So in our case of, let me just go ahead and open Excel to illustrate this. In our case of H2O, what a composition matrix will look like is it'll have the element properties of, let's see, it'll have the element properties across this row. So this actually, let me actually reset here. So if we were to look at element properties, we have atomic number, we might have row, we might have period, we might have atomic radius. So what the composition matrix does is if I have H2O in this here, let me just move this over, it's going to have H in the first row and O in the second row. So my composition matrix will have that saved, and then self.count matrix is going to have, so this would be our composition matrix for all the different features we include. Self.count matrix, it's just going to tell us how much H we have and how much O we have. So these are saved as attributes to the object when we go through this loop. And the count matrix for every single item in the data set, it's going to count how many of each element there were, and it's going to build the feature matrix for each formula in all rows. So this is generate composition matrix. What this does is you give it the element property sheet it wants to look at. You tell it whether or not you want to drop duplicate compositions if they appear in the submitted file. So if you want to drop duplicates, you go through some quick logic to drop your duplicates. Then you read in the element properties. You get the index of each of the element properties. You're going to drop the column elements, so we don't want the strings in there. We only want to be dealing with the actual numerical values, so it would be here. We extract the symbols, which were stored in the index of the CSV. So imagine this column actually became the index, so we can extract these without explicitly having them in the data frame. And then for the, if there's any elements that are missing, we essentially say, okay, for all symbols that do exist, figure out the ones that are found in our actual data set. So in the element properties, some of these element properties won't have all of the elements in them. So if we go here, let me just show you an example really fast. If we go to Magpie, we can look in the atomic number column, and we'll see that we only go up to 97. So there's definitely missing stuff outside of here, and sometimes people actually use this. And other people might even be missing some in here, like they might not have uranium or something. So what we're going to say here is, based off of the element properties index, we're going to make a list of all of the element symbols in the element property sheet that was submitted, and we're going to make a list of all the element symbols that exist, which comes from up here. And we take the difference of those lists to say what elements we simply can't featurize because we don't have element properties for them. And then we keep track of a bunch of information here. We're going to figure out what the column names were. So if we go back to Magpie, they have their column names stored up here. We're just going to store that information so that after we featurize, we can return what columns were associated with what element properties. And then what we're going to do is for all of the different index values, so for every element, we're going to check. Let me just go back here. We're going to check in the data frame that had the submitted data. So if we go back here, you remember when I said we initialize our featurizer? We're going to read in someone's CSV file, and these are the compositions they want featurized. What we're going to do is for that data frame, grab the index values and locate from each index the formula. So now we're extracting the formula from each row. So this for loop is going to go through each row. So each row grab the formula. And if they've submitted a target, extract the target. So right now it's hard-coded that you need to have your first column named formula and your second column named target. We can change that if necessary later. So we're going to extract the formula and the target. And then if X is in the formula, we're just going to continue. We're going to ignore it. So we can also say if Y is in the formula, if Z is in the formula. So this is that logic we had there. So X, Y, Z. So ignore these ones if they're in there. And then for all of the formula that we were successfully able to extract, we're going to get a list of the fractional composition. So we're going to list the elements in this list 1, and we're going to list the count in this list 2. So we have formula mat append list 1 and formula append list 2. So formula mat is going to be a list of all of the formulas associated with each valid row, and count mat is going to be a list of all of the number, or sorry, formula mat is a list of all the elements, and count mat is a list of the count of all of those elements associated with each row. And we're going to have target mat, which is currently a list of all the targets, and formula mat, which is a list of the unparsed formula. Okay, so what we've done in this loop is we've gone through every row in the submitted data, checked if it was valid. If it was valid, we got the list of elements and the list of element counts, and we appended all those lists. Okay, so now we're going to make a matrix that has the formula. We're going to make a list of all the different matrices we're going to be working with soon, and then we're going to make a list of element information. So these are the symbols. These are going to be the indexes associated with those symbols. So if I give you an atomic number, you can figure out what index that atomic number is and grab the correct row, and then this will tell us which ones are missing. So if a formula is submitted with one of these missing elements, we can inform the user that that formula had to be dropped due to lack of element properties. And then we run the assign features function. So now we know what matrices looks like. It has the formula matrix, which is essentially the lists of the elements, the count matrix, which is the list of the element prevalence, the element matrix, which has all of the element properties, and the target matrix, which keeps track of what the actual value was associated with the formulas. Okay, so now if we go here, what we're going to do is we're going to iterate through all of the rows again. So for all of the valid formula we extracted from the user's data, we're going to get a list of those. We're going to get from each row. So H is going to be, this is a range of a length. So H is going to be an integer value. So we're essentially iterating through each row. So for each row in our formula matrix, we're going to list out the elements. So remember, formula matrix had all of the elements as a list. And then for each row in the target, we're going to grab that specific target. We're going to grab that specific formula. And we're going to grab the count. So how many elements there were. So this is essentially saying if we had like H2O, there's an H and an O, so our count is 2. And then we're going to grab our count matrix, which has the prevalence of H and the prevalence of O. And we're going to append that here so that we can do some matrix math there. Okay, so then Our count matrix is just is just a list of all of the counts. Our composition matrix is going to start as a bunch of zeros, and as we build our composition, we're going to fill this in. So for each element in the element list, we're going to, if the element is missing, skip it and append it to our skipped formula list. Otherwise, we're going to extract the row based off of where it is in the element properties CSV, and with that row, we're going to append it into our composition matrix. So, essentially what all of this does up to this point is if element in element list is H, in composition matrix in location I, so the first time through I is going to be 1, or sorry, 0. This is indexing starts at 0 for Python. So for the first time through, if I is 0, that's the first row, and it's going to be assigned the element properties associated with its atomic symbol. So in our case H, it's going to be assigned this entire row associated with H. And then for the next time through, if the element list is I is going to be equal to 1 now, so then our element is going to be oxygen. It's going to extract the element properties associated with oxygen and append them and build this matrix. So that's this composition matrix. Okay, so why do that? Because if we go through this type of logic, we can make the featurization really, really fast. Okay, the last like 15 minutes I hope you just skipped because it was super confusing. I didn't do a great job of explaining it, but if you tried to kind of hang in there and understand what's going on, the most important part is we've built this composition matrix, which is just a matrix that, given your chemical formula, has the elements in it and the properties associated with those elements. And then the second thing that we needed was this count matrix. And that's a matrix that says, given the elements, what were the counts associated with those elements? So really you can think of it more like an array, whereas this is a true matrix. Okay, so now we're going to go to sort, binary, ternary, and I've added another one called generic. So the composition matrix as is represents the elements as they were fed in. I think it might actually be the elements in alphabetical order. I'll have to double check. But it represents the elements in no particular order. So if we want to work with binaries where we want to be able to sort them, we call this sort function. Or ternaries, when we want to sort them, we call this sort function. So what the sort function does is for each of the composition matrices we created, so it's going to look at one of these, it's going to say, okay, I'm going to sort by a specific column you tell me to. So if I tell it sort by atomic number, it'll sort by atomic number. And so it's going to say for each row, essentially, in our composition matrices, so for each instance of data that the user gave us, make a temporary data frame associated with the specific row. So in our case, it'd be this data frame here. So the rows being the elements and the columns being the element properties. And if by is none, so if we sort it, but we don't actually give it an explicit thing to sort, all it's going to do is sort nothing. But if it's not none, what it's going to do is it's going to sort by the column we gave it. So in this case, it's sort of trivial to call sort if you don't put any arguments in, but if you put in an argument such as atomic number, let's say we want to sort in descending atomic number, H and O are now going to swap places. So this is now our new sorted composition matrix. Okay, so this sorted composition matrix can now be used by our binary function or our ternary function. So what this is going to do is it's going to have a list for the features, the formula features, or the formulas associated with those features, and the targets associated with those features. And now again, like we've been doing in the past, we're going to iterate through each row, so each instance of data that was submitted. And we're going to look at the sorted composition matrices and the sorted count matrices. So now what's going to do is it's going to go through, and if the shape is not 2, so if there's So we're looking at how many rows there are in our sorted composition matrix. If there's more than 2 rows or less than 2 rows, if it's not exactly equal to 2, we're going to mark it as non-binary and then skip it. If it is equal to 2, what we're going to do is we're going to start calculating features for it. So sorted comp mat 0, you can see now represents all of the element properties associated with whatever element we've assigned to be A, and then whatever element's assigned to be value B, depending on the sorting, it's going to get all of those element properties. So what we're going to do is we're going to include the counts associated with A and B. We're going to give the values of A and B. We're going to sum up A and B. We're going to take the difference of A and B. We're going to take the ratio of A and B, and I've added an epsilon value here, just so that, let's actually added an epsilon value here, just so that we don't get divided by zeros. And let me just go ahead and add that in explicitly. So I have epsilon there. Okay. Just so we don't get it divided by 0, we're adding in that epsilon. And then we'll take the average and we'll concatenate all those together. So these are individual arrays. And so I'm going to concatenate all of those arrays into one single array. So you can think of, if I were to take the average of this, it's going to go to like maybe 1, 2, 3, 4, 5. And then I do the difference of this, and it's like -1, 3, 1, 2, 23. But these are 2 individual arrays. I'm just going to concatenate them like that with this function here. So I'm going to make a list of what I want to concatenate, and then I'll concatenate all of them along the 0th axis. So I'll concatenate them along their rows. And then this represents the feature of one instance of data, so I'll append all of those together to create a full feature matrix, and then we'll save that as our object's X attribute, and then we'll save the formulas associated with those features and the targets associated with those features as well. And then ternary, we do the same thing. We iterate through all of the sorted composition matrices. And then if it's not equal to 3, we continue. We tell them there was a mistake eventually, and then we go through all the different featurization steps. So this is going to take the max along axis 0. So it's going to look along this axis and say, what's the max of these 3? What's the max of these 3, etc., etc. So then we'll do the min of that. And then once we have the first max and the first min, the second max and the second min, because it's ternary, are the same thing. But we'll go ahead and compute those. This does so by subtracting out the first max, so that everywhere that was a max is going to have a value of 0 explicitly. And then we take that value of 0 and we make it extremely negative, so that it's not going to be marked up as a maximum value lever. And then for our second max, we take the max of the new list, and then we add back the first max so that we get the actual value. That same logic works for second min, but you can kind of go through that yourself. So now we have first max, first min, and second max. So we're going to use these using the same logic you did on your sheet. So first we get the values of A, B, and C. Then we get the sum of A, B, C. We get the difference of A, B, C. We get the ratio of A, B, A, C, B, C, average A, B, A, C, B, C. Take the sum of the 2 maximum values, the sum of the 2 minimum values, sum of the 2 max, 2 min, ratio 2 max, 2 min, average 2 max, 2 min, blah, 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 blah. And we concatenate this list. And what we do is we concatenate the count, so that tells us how much of A, B, and C there was. And we concatenate all of these individual ones along that first axis. And then that results in the feature associated with each row in the submitted data, and that feature is then saved to attribute X. And then for generic, instead of concatenating all of those, what we're going to do is we're going to calculate, I should go ahead and change these so they're not, whatever. So for generic, we're not going to do any sort of real sorting, or rather sorting doesn't affect the generic version. So what we're going to do is we're going to get the counts. We're going to get the sum vector, which is the sorted composition matrix, times the number of each thing in there. So this is array math in order to get, so in our case, if this was 1, 2, 3, 4, and this is 1, 2, 3, 4, and this count is 2 and 1. What this does here is it multiplies this by, let's go ahead and get this in the right order. So it multiplies this value by 2, so that becomes 2, that becomes 4, that becomes 6, that becomes 8, and then this value by 1, so those remain the same. So if this is our count and this is our sorted matrix, this logic here gives us the sum, and then we take that sum and we divide it by the total shape of the sorted matrix, which I just realized is wrong. We divide that by counts, the sum of the counts. So this will give us the average, which is just essentially equivalent to normalizing the formula and then taking the sum. And then with that, we take the sum vector and we add it up. We take the average vector and we take its mean, which is equivalent to summing it. We find the range of the sorted composition. So we can actually take, so this is the range of the element properties. So how far apart is the largest difference in element properties. We take the variance of the element properties, which is like the statistical variance of the element properties for that, for the submitted formula. So variance is sort of trivial when there's just 2, so not really great. But if there's more than 2, this one might actually be useful. And then we just concatenate those the same way we concatenate everything else, put them in a list, concatenate them, and that represents the feature for any specific row in the submitted data. All right, that should be it. I may do a few more updates to this sheet, but hopefully that walks you through it in a way that sort of helps you understand it. See you later.